Okay, so we're going to talk about Newton's law of gravity. And there's an equation. Gravity is described by Newton with an equation, so we'll go over that equation and how to use it. We'll show how that equation allows us to weigh the Earth, and how a guy named, a British experimental physicist named Cavendish did an amazing experiment, and with that experiment he actually weighed the Earth. We'll talk about how to use Newton's law to calculate the acceleration of gravity, not just at the Earth's surface, but any distance above the Earth's surface, right? As you get way above the Earth's surface, obviously, gravity gets less and less. Well, using Newton's law of gravity, we can figure out exactly what the acceleration of gravity is going to be at any distance above the Earth's surface. And then we're going to talk about orbital velocity. How fast do you need to go to be in orbit around the Earth? So that's what we're going to cover here. Pretty cool stuff. All right, so let's talk about gravity. We all know what gravity is, right? If you pick an object up, right, and you drop it, it falls down every time. Okay, and you may not think this is all that exciting, but you did it one time when you were about a year old, and you were sitting in your high chair, and you were just getting to use your arms and legs. You were figuring out, hey, I can manipulate the world. I can use these arms and hands to pick stuff up and throw things. Well, I remember all three of my kids went through this phase where we would put, like Cheerios or something on their table, and they would eat all these Cheerios, and then they were full. They didn't want to eat anymore. And babies are smart. They're smarter than adults because I keep eating, okay, even when I'm full. But babies, when they're full, they stop eating. And so all three of my kids, they would pick something up, and then they would hold it over the edge of the chair, and they would drop their food, and they would laugh, and then they would look over the edge, and it fell down. Gravity was something that they discovered. Hey, every time when I drop something, it falls. Now, that's pretty interesting. Why should, if I pick a ball up and I hold it above the ground and release it and it falls down, why should that happen? Now, most people say, well, that's just the way the world is. But a physicist or a scientist wants to say, why is that? And so Newton was, he knew about, everybody's known about gravity forever. But he also looked at the moon, and he said, well, there's an object that's above the Earth's surface. Why doesn't it come falling down just like an apple falls from a tree? Why doesn't the moon fall and crash to the Earth? But he also knew that the moon circled the Earth. And he had already developed his three laws of motion. And so he started an intense period of thought and work, and he came up with an amazingly useful idea, an expression, a mathematical model that describes how gravity works. And this is what he said. He said, if you take two objects with mass, we'll call this object 1 and object 2, might be over here. This could be the Earth and the moon, but it can be any object. The two of you sitting next to each other right now. You're two objects. You both have mass. Two objects that have mass. I hate to tell you this, and I'm not trying to start any kind of emotional deal here, but you are attracted to each other. Any two objects that have mass apply equal and opposite forces to each other. Now, why this is? Why do massive objects apply forces to each other? Newton famously said, I feign no hypothesis. That means, I don't know. I don't know why objects that have mass are attracted to each other. I just know that they are. And I've described this attraction with this equation, and this equation predicts exactly how the universe behaves. And that's good enough for me. Now, a couple hundred years later, a guy named Albert Einstein came up with a new law of gravity called general relativity. And he kind of went in a little more deeply as to why objects that have mass attract each other. It's because objects that have mass distort the space-time continuum around themselves in such a way as objects want to fall together. We're not going to cover that mathematical model because you basically need to be a graduate student of physics to do that mathematical model. Newton's mathematical model that describes gravity is much simpler, and it's very, very useful. It works. It's still used, so that's why it's taught, even though it's not really the official accepted model of gravity anymore. It still works so well that we still teach it. So this is the force of gravity between these two objects. Now here's what Newton figured out. It's directly proportional, this force of gravity is directly proportional to this mass. Call it M1. If I double M1, I'm going to double the force of gravity. The same is true with M2. If I double the mass on this object, I would also double the force of gravity. If I doubled both of them, it would be 4 times as much gravity. I would double the doubling. Then the distance between them, and we measure the distance between two objects from their centers. There's the center of the Earth and the center of the Moon. I'm going to call this distance R. We call it R because it could be the radius of the orbit or whatever, but you can use the letter D. A lot of textbooks use the letter D for the distance between the two objects. I like to use the letter R. Now, if I make R bigger, in other words, if I separate the objects by a greater distance, isn't it intuitive that the gravity is going to get weaker? Which implies that the force is inversely proportional to R. Now, Newton tried this equation out, and it didn't quite work. And what we find is that gravity doesn't get weaker by 1 over R, it gets weaker by 1 over R squared. In other words, gravity gets weaker by the square of the distance. By the way, almost anything that spreads out over 3-dimensional space gets weaker by the square of the distance. My voice right now, I'm sending out sound waves, right? And those sound waves are spreading out in 3-dimensional space. Well, the volume, the sound gets weaker by the square of the distance. If you have a flashlight, that light is spreading out over 3-dimensional space, so it will get weaker by the square of the distance. So this is kind of a property of 3-dimensional space, that if something spreads out over 3-dimensional space, it gets weaker by the square of the distance. Now, these are the only things, the M1, M2, and the distance between them, these are the only things I can do that will affect how strong gravity is. But if you look, this is measured in newtons. These are in kilograms. This is in meters. Well, kilograms squared per meter squared, that's not a newton. So he knew that there had to be a number that I would multiply this by, a constant of nature that we are going to multiply this by to make the units work and the numbers work. And we call it big G. And big G is called the universal gravitational constant. And Newton had no idea what this number was. He just knew that there had to be one. Now, let me tell you what I'm going to tell you what the value is here in a minute. But what is a constant of nature? Well, it's a property of our universe. You've dealt with some constants of nature before in chemistry, like the mass of a proton. It's the same for all protons. That's a constant of nature. The charge on an electron is a constant of nature. And this number right here is a constant of nature. And what it is, it's a number that describes how strong gravity is, at least in our universe right now. And it's the same everywhere in the universe, as far as we know. And it just tells us how strong gravity is. Now, this is Newton's law of gravity right here. And I'll just tell you what big G is determined to be. G is equal to 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. Now, this looks like a big number to write down. It is. It's a lot of stuff to write down. It's a tiny number. 6.67 times 10 to the negative 11. Negative 11. That's tiny. Newton meter squared per kilogram squared. Now, let me show you how tiny that is. If I took a 1 kilogram mass and put it 1 meter away from another kilogram mass, the attraction, the gravitational attraction between these two, well, look, if I put these on a tabletop, I'm not going to see these things sliding together due to gravity, right? They're not going to just like come together. Why? Because the force is so weak. Just put the numbers in. This is 1 kilogram times 1 kilogram divided by 1 meter squared. Well, what's 1 times 1 divided by 1 squared? This is all 1. 1 times G is 6.67 times 10 to the negative 11 newtons. Okay, what is that? I'm going to move the decimal over to make it times 10 to the negative 12. That's 66.7 trillionths of a newton. In other words, it's tiny. The force between these two objects is tiny. Yes, you are gravitationally attracted to the person you're sitting next to. So, take a look at the person next to you and think of that gravitational attraction. Well, don't worry about it. The gravitation, I don't know about other kinds of attraction, but the gravitational attraction is so weak that you won't feel it. Now, if I put these 1 kilogram masses out in space and there's really nothing else around them, this force is there. And if you wait long enough, it might be a couple of months or maybe a couple of years, but these two forces will eventually come together. And this is, of course, this gravitational attraction between particles with mass is what makes stars and solar systems and what holds galaxies together. Gravity is the force that holds everything together, like the Earth. If you could snap your fingers and eliminate the force of gravity, well, Earth will just fall apart. So this holds everything together. And obviously, it holds us down to the ground. It holds our atmosphere down to the ground. I mean, if no gravity, no atmosphere. If you have a planet like the moon has very weak gravity. It has no atmosphere. Its gravity is not strong enough to hold an atmosphere down. So be grateful for gravity. It allows us to breathe. Now, who figured this out? Well, a guy named Cavendish figured out what this is. Because here's what you have to do to figure out what the gravitational constant is. Well, take the law of gravity. And say, well, I know that this is true, or at least Newton proved that this is true. Solve for G. let's solve for the gravitational constant. Do a little algebra 1 here. G is equal to the force of gravity times r squared divided by the masses. Now this tells you what experiment you need to do. You need to find two massive objects of a known distance apart, measure the force of gravity between them. How much attractive force is there between these two objects? Plug all your numbers in and out will pop the gravitational constant. The problem is that experiment is really hard to do. You need an exquisite experiment to do it. And long after Newton died, this other British guy, figured out, created an experiment, and that actually allowed us to solve for G. And here's what he did. And this is a way oversimplification. Imagine you've got a barbell-like thing. Okay, here's a very light little bar between them. And you're going to hang this by a wire from the ceiling. Okay? Now this thing is able to swing around. Then what you do is you put a little mirror right here on the wire. And you take a little beam of light. And you take the beam of light and it comes down, it hits the mirror, it bounces off, and it puts a little spot of light on a wall over here somewhere. Then what he did is he put another big, metal sphere in front of this one and behind this other one. Now, these were big objects, but even big objects apply very, very tiny forces of gravity. But there was a little bit of gravity here. A little tiny force of gravity between these two. Barely noticeable. Now, when you put these near, it's going to apply a force to this guy and a force to this guy. And what's that going to do to the wire? These little tiny forces. It's going to twist the wire. It's going to twist the wire a little bit. It's going to apply what we call a torque to this. Now it's a very tiny torque, and you could barely even see the torque. I mean, if you were just looking at the barbells, you wouldn't even notice it. But you would notice this little beam of light, because when you put these right here and here, it torques just a tiny little bit, and it changes the angle of the mirror a little tiny bit, and it changes where this beam hits the wall a little tiny bit. So instead of being here, now the beam of light is hitting here, and now all of a sudden you can figure out how much torque there was. And if you know how much torque there was on this wire, you can figure out, and you know how far apart these things are, you can figure out what these forces of gravity are. Basically he went through a series of calculations that allowed him to measure the force of gravity between two massive objects where you know what the masses are and you know how far apart they are. He measured this. He measured the force of gravity. This was something that Newton could not do. But Cavendish did it. And when he did it, he plugged in his force of gravity and the distance apart between the massive objects, and he plugged in their masses, and he got this number right here. Now, by doing so, he measured the mass of the Earth. We can calculate the mass of the Earth. And here's how you do it. Here's the Earth. And here we are. Here you are, standing on the Earth's surface. Now, we know if we have you standing on a bathroom scale, right, we can measure the force of gravity. And that's just your weight in newtons. Okay, that's your force of gravity. So we can measure the force of gravity between you and the Earth quite easily. Just get a bathroom scale. Now, we know the radius of the Earth. There's various ways of measuring that, but let's just say that we know what the radius of the Earth is. So we know what your mass is. Let's say we know what your mass is, we know what your weight is. These are things that are easily measured. We know what the radius of the Earth is, so we know the distance apart between you and the center of the Earth. And so what we can do is we can take Newton's law of gravity, and which is G m1. Now let's just go me, the mass of the Earth, over, and I'm going to call it r squared, capital R, that's the radius of the Earth. We'll just solve it for the mass of the Earth. So the mass of the Earth is equal to your weight times the radius of the Earth squared divided by G, and this is what Cavendish measured for us. Without Cavendish, we couldn't do this calculation. And divided by your mass. Well, you plug these numbers in, figure out what your weight is in newtons, the radius of the Earth, big G, and your mass, and out comes the mass of the Earth. And here it is. When you do this, the mass of the Earth is 5.98 times 10 to the 24 kilograms. Now, I hate to tell you this, but in this unit on gravity, you need to use scientific notation, because we're dealing with big numbers and tiny numbers. Numbers that are so big and so tiny that you really need to use scientific notation. And it's kind of a pain in the neck. But sorry, that's just the way it is. Okay, now we're going to derive an expression for how fast do you need to go around the Earth and not fall down, to be in orbit around the Earth. And using Newton's law of gravity. So imagine here you have the Earth, okay? So here's the Earth. Now imagine that I'm standing here on top of the Earth, okay, not drawn to scale, okay? And I've got a big cannon. So here's my cannon. It's like a pirate's cannon or something like that. And I'm going to shoot cannonballs out of this cannon. Okay? Why? Because it's fun. Have you ever been to go to a Civil War reenactment someday and watch them shoot off the cannons? It's loud. All right. So you fire a cannonball. Now what does gravity do to the cannonball? It pulls it down to the surface of the Earth. Right? So, all right. So there it goes. You just fired the cannon and hit the ground. Well, put in more powder. Put in more gunpowder so that that cannonball comes out going much faster. Now gravity is still acting on this cannonball. Okay, maybe it hits the ground over here. Now notice that if it hits the ground over here, it's no longer in my line of sight. The curvature of the Earth is now blocking my view of where that cannonball hits. This happened during World War II. Battleships had these great big cannons that would shoot projectiles so far that they couldn't see where they hit because the curvature of the Earth was in the way. Okay, so now whatever's worth doing, it's worth overdoing, right? Let's put in more powder and really fire this this cannon so it goes super fast. So it fires. Okay. Antarctica. No more March of the Penguins. Okay. Wiped out a whole endangered species there. Look. Not quite fast enough. Okay, so now we're going to shoot a cannonball out of this cannon so fast okay, so gravity is pulling this thing down, but it's going so fast that it matches the curvature of the Earth. So finally, I shoot myself in the head. Okay, the cannonball went all the way around. Now, if I duck, it won't hit me in the head. It'll just keep falling around and around and around. So if an object is in orbit, gravity is trying to pull it down, but it's moving so fast in a horizontal direction that the curvature of what it's in orbit around matches the curvature of the orbit, and it never hits the ground. Now, there is a problem with this if I try to do this near the Earth's surface. And what is that problem? It's called an atmosphere. If the atmosphere is present, and here on the Earth's surface we have an atmosphere, this cannonball would come out so fast that it would compress the air in front of it. It would squish in the air. And if you remember from chemistry, when you did ideal gas laws, what happens when you very suddenly compress a gas? It gets hot. It gets really hot. It would get so hot that heat would radiate into the cannonball, and in a very short period of time, it would vaporize it. Okay, this is what you see when you see meteors hitting the Earth. You know, at night you look up in the sky and you see a meteor flash by. Well, that's a little grain of sand, basically, hitting the Earth's atmosphere, compressing the air in front of it, and the heat from that compressed air, it's not really friction, it's compressed air, it vaporizes it. And you see it as it vaporizes it as a bright light streaking across the sky. When the astronauts come back to Earth, they have to have a heat shield to protect their spacecraft from the heat of this compressed air as they come in at super high fast speeds. You've got to go really fast to be in orbit. And we're going to calculate that speed here in just a minute. Well, when you launch a spacecraft, here's the curvature of the Earth. Now, here's the atmosphere. Okay. Now, when you launch a spacecraft, like the space shuttle, where we used to launch space shuttles, or satellites or whatever, here's our rocket, it launches. The first thing you got to do is go up. Why do you need to go up to be in orbit? Because you got to get above the atmosphere. Because you can't go fast enough to be in orbit if you're in the atmosphere. So you go up, up, and up. But then, very quickly, you start seeing the spacecraft pitch over. And pitch over because now it needs to not only go up, but it needs to go fast horizontally. It goes up, 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 and then finally it's above the atmosphere now. So it doesn't need to go up anymore if this is a low Earth orbit, but it needs to keep it firing its engines for a few minutes until it gets up to that very special speed where you'll go fast enough where the curvature of your path, because of the pull of gravity, matches the curvature of the Earth. Okay, and that's orbital velocity. Now, let's figure out what that velocity is. And it's really not very hard. Here's the Earth again. Now, let's suppose I've got a satellite in orbit around the Earth. And it's moving in a circle. Not a very good circle, but it's moving in a circle. So here's here's our planet. Now this could be a star, it could be Earth, it could be the moon, whatever. Now here is the radius of our orbit, r. And we're falling around the Earth. But what kind of motion is this? I'm moving in a circle. What kind of force makes things move in a circle? A centripetal force. So in other words, the force of gravity is equal to a centripetal force, which we know is mv squared over r. Well, we now have an equation, though, for the force of gravity. The force of gravity, well, let's call this big M. That's the mass of my planet. Let's call this little m. That's the mass of my spaceship. R is the radius of my orbit. So I can say that the force of gravity is equal to the universal gravitational constant times the mass of my spacecraft times the mass of the planet divided by the radius of my orbit squared is equal to mv squared over r. Now, when you're in circular orbit, the force of gravity is a centripetal force. All we need to do now is solve for v, and that will give us our orbital velocity. That cancels. The mass of my spacecraft cancels. It doesn't matter how big or small your spacecraft is. Your orbital velocity will be the same. Solve for v. So v is equal to, well, it's already solved for v squared, so all I got to do is take the square root of this. And this, I'm going to put v sub orb. This right here is my orbital velocity equation. And I love this equation. This equation tells me how fast I need to go to be in orbit around anything, whether it's an asteroid or a star, a black hole, a galaxy, whatever I'm in orbit around. If I know what the mass is and I know how far I am from the center of that object, I know what the universal gravitational constant is. Thank you, Cavendish. I can figure out how fast I need to go. When you plug the numbers in to be in Earth orbit, a low Earth orbit, and we're going to do this as an exercise in the homework, but but to be in orbit around the Earth, you need to go really fast. It's about 17,500 miles per hour. 17,500 miles per hour. Okay, that's about 5 miles a second. Here to Selma in 2 seconds. You can circle the Earth in 90 minutes. The space station that's in orbit right now circles the Earth every hour and a half. So that's pretty cool. So now I can also, by the way, use this equation here, Newton's law of gravity, to figure out what the acceleration of gravity is for anywhere I want to be around the Earth or the Moon or anything. So that'll be the last thing we do here. So again, here's the Earth. Now here's my object. So here's M, and here's my satellite or my spaceship M, and maybe it's not even in orbit. I don't know. It doesn't have to be in orbit for this to be true. Just be some distance r from the Earth. Well, I want to know, what is this force of gravity? Here's my force of gravity acting on that object. Well, this force of gravity, well, it's equal to the mass of my spaceship times g, my gravitational field or the gravitational acceleration for this object. Now, here's why this object doesn't move in a circle. It's so big, the Earth is so big to my little spaceship, my satellite, that you don't see the effect of this force on the Earth. It exists. The Earth wobbles a little bit, but it's so tiny we're just going to ignore it. So this thing is just going to be out there, and it's going to be accelerated. Now, this force of gravity, though, is also equal to G m over r squared. So the force of gravity on my satellite here is equal to m times g. But it's also equal to g, a big G, gravitational constant, times the mass of the Earth, times the mass of my satellite, over r squared, the distance from here to here. Well, all you got to do is cancel out the mass of my satellite, and I've got an equation for the acceleration of gravity above the Earth's surface. The acceleration of gravity above the Earth's surface is equal to big G times the mass of the Earth over r squared. It's pretty simple, actually. Now, if you plug in the mass of the Earth and big G and the radius of the Earth squared, plug that all in, guess what you're going to get for G at the Earth's surface? You're going to get 9.8 meters per second squared. Okay, one last thing here. The radius of the Earth, quite often they'll give you an altitude. And an altitude is a distance above the surface. So to get the radius of my distance, r is from the center of the Earth to my satellite. Well, what do I, if they give me h, and h is going to be the distance from the Earth's surface to my satellite, that's going to be the radius of the Earth or the Moon or Mars or whatever planet we're looking at, plus my height above the surface. So you have to remember to use this equation. Okay, let's summarize all the equations you need. And by the way, this is everything you need for the gravity unit that we're doing. Well, I can express just about everything in one line. The force of gravity is equal to, well, first of all, it's equal to mg. That's still true, where this is the acceleration due to gravity. Mass times acceleration is a force. But it's also equal to big G times the mass of my planet or whatever, times your mass or the mass of your spacecraft, over r squared. And if you're in circular orbit, it's equal to mv squared over r. It's a centripetal force. Now remember, this is only true if you're moving in a circle. When you solve this for v, you get my orbital velocity is equal to the square root of gm over r. You can also solve this for the acceleration of gravity. So the acceleration of gravity, when you cancel this little m out, is gm over r squared. And you should also know that r is equal to the radius of the planet plus my height above the surface, if that's what they give you. Sometimes they give you the radial, or they give you r, little r. But if they give you the radius of the planet and then a height, you have to add them. One last thing to remember, that the orbital velocity is also equal to 2 pi r over the period. Sometimes they'll give you the period of the orbit and the radius of the orbit, and so you can figure out the orbital velocity using this, and then you can take this equation and solve it for the mass of the planet or whatever. By the way, this is how we know what the mass of a black hole is. If we see a black hole out in space, if we see the black hole out in space, we can't really tell how fast it's, we can't see it. It's a black hole. It's got too much gravity. But we can see objects in orbit around it. And if we know what the radius of that orbit is, and we know what the velocity is, we can solve for m. We can solve for the mass of a black hole. Okay, that's it.